Okay, so as we last left off, we were discussing nomenclature, naming different compounds, be it ionic compounds or covalent compounds. So you need to be able to classify the compound in order to effectively name it. So let's do a few examples and let's work through these examples. So our first goal in this entire process is to classify each of our compounds. So in this case, so MgHPO4, that is clearly an ionic compound containing a polyatomic ion. As such, we name it as a polyatomic ion containing ionic compound. Additionally, this polyatomic ion is hydrogen containing. So we write the name of our metal, which would be magnesium, and then we write the name of our polyatomic ion, which in this case would be hydrogen phosphate. So this full name would be magnesium hydrogen phosphate. Looking at this next example, so iron is a transition metal. And because transition metals can adopt a variable charge, we need to name this compound a little bit carefully. So the name for this compound would be iron 2. Where do we get the 2 from? Well, when we cross the charges, we get Fe2 plus and ClO3 minus. This matches the known charge for chlorate. So we note the charge of iron in parentheses after the name, and then we write the name of our polyatomic ion. So this would be iron 2 chlorate. In the final example, we have hydrogen in a polyatomic ion. This is a polyatomic acid. Because remember, acids are neutral and they contain hydrogen and an anion, be it a polyatomic ion or an atomic ion. So this is a polyatomic acid, and as such, we name it using our acid conventions. So CrO4 2- is known as chromate. The ATE ending turns into IC, following our polyatomic acid nomenclature rules. So this would be chromic acid. So as you notice, the first task in effectively naming a compound is to accurately classify the compound and identify the components in your compound. Does this example make sense to everyone? Does this example make sense? Any questions on this example? So your first goal when naming compounds is to classify them. And as you see, now that we have a range of different compounds that we have to name, it's really important to pay attention to key components of their formula. Is there a transition metal? Is there a polyatomic ion? Is this an ionic compound, covalent compound, or an acid? As all of those compounds have slightly different naming rules. Does this make sense to everyone? Okay, so let's now have you work on these 3 examples. Let's spend about 4 to 5 minutes on these 3 examples, and I'd like you to propose names for the following 3 compounds. Don't be shy to share your proposed names for each of these compounds in the chat, and if you have any questions, don't be shy to share your questions in the chat or verbally, and we'll discuss this example in about 4 to 5 minutes. And let's try to get a few proposed names in the chat or shared verbally before we discuss this example of mixed nomenclature. Remember, your first order of business is to classify your compounds. Once you have your compounds classified, then you can name them following the nomenclature rules that we discussed in this chapter. And don't be shy to share your responses in the chat or verbally. It's really important to tackle nomenclature in the context of mixed nomenclature examples, because often the difficult part in nomenclature is not just coming up with the name, but figuring out what set of naming rules to utilize. So let's keep working on this example and we'll discuss in about another 2 to 3 minutes. And I'd like to see at least a response from a student for each of these 3 nomenclature questions. And really don't be shy to share your proposed responses in the chat. And if you have any questions on naming these 3 compounds, don't be shy to ask them verbally or in the chat.
Can't find MN.
The second one, MN?
Yeah,
And what is your question?
like atomic number, like where is, I can't locate it, MN.
Mn is manganese, and it's a transition metal. Allow me one moment to look up the atomic number. Manganese has atomic number 25. It's right next to iron. Are you able to find it now?
Yes, thank you.
So let's try to get a few proposed names in the chat for each of these compounds, and then we'll discuss momentarily in about another 1 to 2 minutes. And don't be shy to share your proposed names in the chat. And we're starting to get some proposed names in the chat for these different compounds. Let's keep working on this problem. Let's try to get a few more responses, and we'll discuss in about another minute to a minute and a half. Okay, so let's discuss this example. Aluminum is a group 3A metal, and hydroxide is a polyatomic ion. So as such, we name this as a polyatomic ion containing ionic compound. So we write the name of our metal, which is aluminum. Now, since aluminum is a main group metal and not a transition metal, we don't have to state the charge. The charge is known. Then we write the name of our polyatomic ion, which in this case is known as hydroxide. So this compound would be named as aluminum hydroxide. Okay, continuing on, looking at MnO2. So first and foremost, manganese, Mn, is a transition metal. And as such, we need to specify the charge. So if we take a look at MnO2 and we reverse cross our charges, that gives us manganese 2 plus and O minus. However, we know that oxygen is known to have a 2 minus charge. So then we multiply each of our charges by 2, and that gives us manganese 4 plus and O2 minus, which matches the known charge of oxygen. Now that we have the charge established, we can name this compound. So we write the name of our metal, which is manganese. We specify the charge in Roman numerals, which would be 4. And then oxygen is named with the IDE ending, as we're dealing with an ionic compound with a non-metal anion. So this would be manganese 4 oxide. Does this example make sense to everyone? Any questions on this example?
Yes, Professor. When it's a transitional metal, is that when we multiply only at that time or no?
So the transition metal simply denotes that we have to specify the charge with a Roman numeral. The reason why we multiply is when we reverse cross our charges, we get a charge of -1 for oxygen. And that does not match the known charge of oxygen in our periodic trends. So to correct that, we multiply both of our charges by the same number, in this case 2, so that the charge of oxygen matches the correct charge predicted from periodic trends.
Okay, so basically it has nothing to do with transition metal, only because of the fact that it has a negative on the oxide.
Yep,
That's
exactly.
correct. Okay.
Exactly. The only part for the transition metal that's important is you have to specify the charge using a Roman numeral.
Okay, got it. Thank you.
Mm-hmm. So looking at the next portion of this example, HClO2. HClO2, this is an acid. More specifically, it's a polyatomic acid. We have hydrogen and a polyatomic ion. So looking at our polyatomic ion, ClO2 is known as chlorite. Ite turns into OUS, so this turns into chlorous acid. You have to know the name of your parent polyatomic ion in order to name polyatomic acids. Does this example make sense to everyone? Does this example make sense? Any questions on this first example?
Professor,
If not, yes.
this, the last one for the polyatomic acid, how
Yep.
come we don't put the hydrogen on it?
The hydrogen prefix is only reserved for binary acids, which contain hydrogen and an atomic ion. For polyatomic acids, we do not put the hydrogen or hydro prefix.
Okay, got it.
Does that make sense?
Yes, thank you.
Perfect. So let's do a case where we have to write the formula from the names. So I'll do the first three, and then you'll do the next three. So we have iron 3 nitrate. So following my rules, I write out each of my ions. In this case, I know iron has a 3+ charge. Nitrate is NO3 minus. I cross my charges, and that gives us FeNO3 3. So this would be the formula for iron 3 nitrate. Looking at this next example, acetic acid. So this is derived from acetate, which has the form CH3CO2 minus. Acids contain our ion and H plus. So then I cross my charges, and that gives us CH3CO2H. You can also write this as C2H3O2H, though I would prefer if you write it in this top manner because it'll be much more useful when we get to the organic chemistry section of this course. Remember, acids contain an ion, be it a polyatomic or atomic ion, and hydrogen. And we can figure out the number of hydrogen atoms by crossing the charge of H plus and our polyatomic ion.
Can we put the H in front of the acid?
You can. The reason why I wrote it this way is that it's more descriptive of the actual structure. But yes, you can. Any other questions on this example? In the next case, we have ammonium oxide. So ammonium, that's a polyatomic ion. So ammonium has the form NH4 plus. Oxide has the form O2 minus. We cross our charges, and that gives us NH4 2O. So this would be the formula for ammonium oxide. Do these examples make sense to everyone so far? You're going to really want to be familiar with the polyatomic ions and your different sets of nomenclature rules to tackle these mixed nomenclature problems. So let's look at the next example, and I'd like you to take a look at the following three names, and I'd like you to write the formula for each of these three compounds. And we'll give everyone about 4 minutes to work on these examples, and we'll discuss these examples momentarily. And if there are any questions I can address as you work through these examples, don't be shy to ask them in the chat or verbally. And let's try to get some proposed formulas for each of these different compounds in the chat, and then we'll discuss. And if you have any questions naming these compounds, don't be shy to ask in the chat or verbally, and we'll discuss in about 2 minutes. I'd really like you to share your responses in the chat because it's important before you see the solution and before we discuss the solution to a problem to have your own thoughts and ideas about how to go about solving the problem. So when you see the solution, you can revise your logic. And I find this process of revision after proposing your answer, proposing your names or formulas for these compounds is where you get the most benefit from these exercises. So we'll discuss these examples in about another minute to a minute and a half, and don't be shy to continue to share your responses in the chat. And let's try to get a few more responses in the chat, and we'll discuss in a minute. Okay, perfect. We have a nice pool of responses, so let's discuss. So for cesium hydrogen sulfite, okay, so cesium, so we have cesium plus because it's a 1A main group metal with a charge equal to its group number, which is +1. For hydrogen sulfite, sulfite is SO3 2 minus. If we add a hydrogen, we get HSO3 minus. Crossing the charges, our final formula gives us CSHSO3 for for cesium hydrogen sulfide. Does this example make sense to everyone? Remember, for hydrogen-containing polyatomic ions, when you add a hydrogen, your charge goes down by 1. Let's look at this next example. Hydrochloric acid. This is a binary acid. We can tell by the hydro prefix. So chloric is derived from chloride. So to write our formula, we take H plus and we cross our charges with Cl minus. So this hydro prefix tells us we have a binary acid. And so our formula would be HCl. Do these examples make sense to everyone so far? Remember, the hydro prefix and the hydrogen prefix is unique to binary acids. Just to show you for comparison, chloric acid would have the formula HClO3. So the subtle difference of a single prefix can dramatically alter your final formula. Does that make sense to everyone? Does everyone see that distinction?
Yes.
Perfect. So let's keep going and let's look at this next example. So for xenon tetrabromide, this is a covalent compound. This tetra prefix is a huge giveaway. We're dealing with a covalent compound. So we write xenon, and bromide is referring to bromine, and tetra tells us we have 4 bromines. So this would be the complete formula for xenon tetrabromide. Does that make sense to everyone?
But then how their charges would not be balanced?
But for covalent compounds, you're not dealing with balancing charges in this case because we don't have ions. Rather, we are sharing our electrons via covalent bonds. And as a result, there's no charge to balance per se. Rather, our final structure simply has to fulfill the octet rule. Does that make sense?
Yes.
Perfect. So we've covered mixed nomenclature. Let's now talk about organic nomenclature. And we'll go into more detail later on in this class when we start to talk about organic compounds. But for now, let's introduce the basic principles behind organic nomenclature that I'd like you to be familiar with and I'd like you to be exposed to so we have this knowledge prepped for later portions of the class. So organic compounds, these are molecular compounds composed primarily of carbon, hydrogen, nitrogen, and oxygen. These are the majority of biologically relevant compounds that we'll encounter and that we'll discuss in this class. And let's talk about the first major class of organic compounds, which are known as alkanes. These are saturated hydrocarbons. They contain only carbon and hydrogen and only single covalent bonds. Now, alkanes have a unique formula of the form CnH2n plus 2. So for example, CH4, C2H6, C3H8, these are all common formulas of alkanes. Now, to name these alkanes, it's really quite simple. You write a prefix, and this prefix designates the number of carbon atoms. Then, once you have your prefix in place, once you have your prefix established, then you add the ane, A-N-E suffix. So for example, C3H8, so we first count our number of carbons. So we have 3, so we use the prefix of prop. Then, since it's an alkane, all we have to do is add the ending of ane. So prop prefix turns into propane. Does this make sense to everyone? So remember, you're going to need to memorize these prefixes for organic compounds. But beyond that, all we're doing is writing the prefix and the ending of ane. So for example, let's try to answer this question. Would someone like to tell me what is the formula for heptane? What does hept tell us?
7.
Yep, so we have 7 carbons. So if we have the formula CnH2n plus 2, so we have C7H2 times 7 plus 2, that would give us C7H16.
Why do we need the 2 times 7 plus 2?
Ah,
Is that the formula?
this formula, it allows you to calculate the number of hydrogens given the number of carbons. And the reason why this formula works, so for example, for propane, is that to satisfy the octet rule, we need each of our carbons to have 4 bonds. As a result, if we only have hydrogens to work with, we need 2n plus 2 hydrogens compared to our number of carbons. This stems from fulfilling the octet rule. Does that make sense?
Yes.
Perfect. Now let's look at our next variant. These are known as alkenes. These are hydrocarbons with fewer hydrogens than alkanes because they are unsaturated. They contain double bonds. So a common example of this would be ethylene. Alkenes have 2 fewer hydrogens than alkanes. We lose 2 hydrogens per double bond. So an alkene has a formula of CnH2n. Now, remember, alkenes are denoted by the presence of a double bond. Okay, so if you see a double bond and only carbons and hydrogens, you're dealing with an alkene. So to handle an alkene, just like before, we write the same prefix for the number of carbons, and then we add the suffix of ene. So for example, C2H4, so we have 2 carbons, so we use the ethyl prefix, and then we add the ending of ene. So C2H4 would be known as ethylene. And that looks something like this. C3H6, we have 3 carbons, so that's propene. And depending on how it's and propene looks something like this. Do the rules for naming alkenes make sense to everyone? Well, to check and make sure, I'd like you to tell me, what is the name of C4H8? C4H8. Would someone like to volunteer the name verbally or in the chat?
Butene?
Yep, exactly right. So 4 carbons, we use the prefix but. Since we have the formula CnH2n, it's an alkene, so we write this as butene. And butene, well, there are variants of butene, but probably the most common variant looks something like this. Does this make sense to everyone?
Professor, where do you get the E? I get where you
Oh,
get
because it's an alkene, which has the formula CnH2n, because we have a double bond, that's when, and because we have a double bond, it's an alkene, and as a result, we use the suffix ene to denote we have an alkene. Does that make sense?
not really, but I'll keep looking at
It's based on the number of hydrogens in the formula. If the formula is of the form CnH2n, then we have less hydrogens than a typical saturated alkane, and as a result, in this case, we have a double bond. The presence of a double bond in turn requires us to name our compound as an alkene rather than an alkane. So rather than butane, it would be named as butene. So to help you compare, C4H10 is known as butane. CnH2n plus 2 is its general formula. Butane looks something like this. Does everyone, do you notice how the main difference between these two formulas is the presence of a double bond? If we have a double bond, we name our compound as an alkene. So rather than butane, it's named as butene. Does that make sense?
For the last formula you showed, that was butene
Or
butane, I'm sorry.
Yeah, so we have butane, C4H10, butane, C4H8. We lost 2 hydrogens when we formed our double bond. Does that make sense? So the presence of a double bond functional group requires us to name our compounds in a slightly different manner.
How do we know if they have double bond or not?
Because the formulas are different. The formula of an alkene is CnH2n, while the formula of an alkane is CnH2n plus 2. So the number of hydrogens relative to the number of carbons directly tells you whether or not you have an alkene. Does that make sense?
Yes.
Perfect. So let's look at our next functional group that we have to deal with. The next functional group that we'll introduce is an alcohol, which is of the form an OH functional group. So the OH group is known as an alcohol functional group. And in order to name alcohols, you write the prefix for the number of carbons, you add the suffix -ane, and then you replace the E with the OL suffix to denote that we have an alcohol. So for example, CH4 would be named as methane. However, since we have an alcohol functional group, instead of methane, we name this compound as methanol, where this ane is telling us we have the form CnH2n plus 2, and this OL suffix indicates we have an alcohol functional group. Does that make sense to everyone? So we replace the E in our ending with the OL suffix. So let's look at another example. So we have CH3CH2OH. So we have a formula C2H6O. So if we have 2 carbons, what prefix do we use? 2 carbons, what prefix do we use?
F.
Yep. So this will be F. We have the formula CnH2n plus 2. So we name this as ethane. However, because we have an alcohol functional group, rather than ethane, it would be named as ethan. What do we put at the end? What suffix do we put? If we have,
OL.
yep. So instead of ethane, it would be ethanol. Just to show a side-by-side comparison.
The all is just because it has the OH, right?
Yep, exactly right. The OL suffix denotes that we have an alcohol. Does that make sense? Perfect, perfect. So I'd like you to try and propose a name for the following compound. Let's take about 2 minutes to work on this example, and I'd like to see a few proposed names for the following compound. Remember to count your carbons. The carbons are key to naming organic compounds. And let's try to get some proposed names for these compounds in the chat or verbally proposed. And we'll discuss in about another minute.
Professor, I'm kind of confused. What do we do with the H again?
What do we do with the H or the OH?
Just the H.
Like what could you elaborate on that?
So I know, so like the first step would be counting the carbons,
Yep.
and then
Yep.
we count the hydrogens next,
Yep.
or?
Yep. Yep. So it's of the form C4H.
10, right?
Yes. So it's of the form CnH2n plus 2. So it follows the typical formula of an alkane. So we can use the AN ending to start.
I guess I'm really confused on that part, but I'll wait.
So this is mainly just a check to make sure you don't have to change your naming convention to an alkene naming convention. For now, this part doesn't affect your final name for this alcohol substantially. It just tells us that we have the ANE suffix preliminarily. And then we modify this ANE suffix when we have an alcohol.
Okay.
Does that make sense?
Yes.
So in this case, 4 carbons. What's the prefix for 4 carbons? 4 carbons, that tells us what? What's the prefix for 4 carbons?
Bute.
Yep. So we name this as bute. It's of the form CnH2n plus 2, so we name it as butane. However, since we have an alcohol, instead of butane, it would be named as butan. What suffix do we use at the end to denote an alcohol?
OL.
Yep, so this is butanol. Does this make sense to everyone?
And you say when it has the alcohol, it's the O in front of it?
The alcohol is denoted by this OH group.
OH group, okay.
Yep. And that's why instead of naming it as butane, we name it as butanol. Does that make sense?
So how do we distinguish that it's that formula? I know you mentioned it a little bit earlier, but the H2N plus 2, how do we know it's the 2N plus 2?
So if we have 4 carbons, then we'd plug in N equals 4. So this has the form C4H2 times 4 plus 2, which is of the form C4H10. So the formula matches that pattern for a typical alkane skeleton.
Oh, got it. Thank you.
Does that make sense?
Yes, a lot better. Thank you.
Okay, so that's it for your brief introduction to organic nomenclature. We'll be covering this a lot more in later portions of the class when we start to introduce different functional groups in the context of biological systems. What we're now going to do is we're going to switch gears and we're going to talk next about chapter 4. And the notes are up on Canvas, so you may want to pull them up on your computer at this time. They're under the week 8 module. They're titled Chapter 4 Notes. So what we're going to do is we're going to switch gears and start discussing Chapter 4.